Today I will be explaining what end behaviors are and what affects them. Here we have our standard cubic equation. With these arrows, end behaviors describe functions as continuous, going past the drawn axes and approaching infinity. From this point here, we can see that both values x and y are increasing forever, going closer or at least approaching infinity. Now we can write the notation as x approaches or increases towards infinity, f of x also approaches infinity. From this point, we could also see that x is decreasing and y is also decreasing. So we could say as x approaches negative infinity, f of x is also approaching negative infinity. Now I will be showing you what factors affect these end behaviors. Here we have our standard quadratic equation. Ax squared plus bx plus c. If a is greater than 0, our graph opens upwards, meaning that f of x approaches infinity both left and right. On the contrary, if a is less than 0, the graph opens downwards and f of x approaches negative infinity on both sides. We must also keep in mind that the degree, or the largest exponent, also determines what the end behavior looks like. Degrees determine how many turning points we have in a graph. To find how many degrees we have, we must subtract our degree by -1. Since we have 2, we subtract it by 1, and we get 1 turning point for the function. Let's say we even had a larger polynomial. Bx cubed cx dx plus e. We could still determine the number of turning points by subtracting 4 by 1 to get 3. So we know that our graph will have 3 turning points. And because it's positive, it opens upwards. However, if a was negative, our graph would reflect downwards. Both of these equations are prime examples of even degree functions. A primary characteristic of even degree functions are that both ends go the same way, as seen here. Now, odd degree functions are slightly more complicated. Here we have a standard cubic function, and we know it's odd because our greatest exponent is 3. If a is greater than 0 in an odd degree function, our graph would look like this. And if a was negative, it would go the opposite way, like this. Here we could see a pattern. No matter how big an exponent is, it's always going to have similar behaviors. Here we have a function with a degree of 7. One obvious characteristic we could identify is that both sides go opposite ways. And this is true for all odd degree functions.